Alright, it's Mr. Noldy back again on Planet Numeracy. As promised, here's a follow-up video that shows you how to do some related rates problems. This is a classic, the pebble drop. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So that's kind of like this. You dropped a pebble here, and it's making concentric circles around the outside. The ripples, they just keep on spreading out this way. So what they're telling us is that there's a constant rate. The radius is increasing at a constant rate of 1 foot per second. So that's a derivative, okay? It's a change. So it's increasing. So I'm going to say dr over dt. So the rate of change in the radius over time is what this means. And it's increasing at a rate of 1 foot per second. Now, in a minute, we're going to use this r equals 4 for when I solve the problem. And let's see, what am I looking for? At what rate is the area, increasing? So that's dA over dt. So that's the change in area over the change in time. So let's start off. This is when you need to do implicit differentiation, because we're differentiating actually with respect to t, where t is the time. Let me jot that down. T is time. So if I'm going to differentiate this, the first piece that I want to differentiate is right here. So I'm going to take the derivative of area with respect to time, and that's going to equal, let's see, 2 pi r, but I have to write down dr dt. So the same way with the x's and y's, when I didn't have an x term, I had to write dy dx next to it. Here I don't have a t, so I have to write dr dt because I'm doing it with respect to t. So now I'm ready to solve this. The dA dt ends up being, after you make your substitutions, 2 pi, the radius was 4, so 2 pi r, 4, and dr dt is given up here as 1. So this is expanding at a rate of, let's see, 8 pi, and because it's area, it's going to have to be square feet per second. And that is just a real quick example. I'll show you another example here. So hopefully you'll get the hang of these the more that you see. But it's just like anything. You have to practice to get good at it. Math is not a spectator sport. So let's look at another example. So a ladder 25 feet long is leaned against a building. The base of the ladder is pulled away from the building at a rate of 2 feet per second. How fast is the top of the ladder sliding down the building when the ladder is 7 feet from the building? So this is a classic problem, and you better believe this will be on my final exam. So 2 feet per second, that's a rate of change that we're looking at. So we want to know another rate of change. How fast is it going to be sliding down the wall when we're 7 feet from the building? So let's draw a building, shall we? There's my building. And here's my ladder. So it's a right triangle. So that's why I drew it this way. But the ladder's 25 feet long, which is a constant. That is not changing no matter what. We want to know, let's see. Oh, I know that my x, I'm going to call this dx dt, I think, right? Because it's saying that the ladder is being pulled away from the building at a rate of 2 feet per second. So I'm going to go ahead and do a dx dt equals 2. And I'll just say 2. I mean, it's going to the right, so that's kind of like to the right on the x-axis. And let's see, what other information are we given? We are given that, well, we want to find out how fast it's sliding down. So that's going to be a variable. That's a rate, dy dt. what is that equal to? That's what we're trying to find out when we are 7 feet from the building. All right. So, this is nice because this is a Pythagorean triple, a 7, 24, 25 Pythagorean triple. A lot of these problems are designed so that if you know your Pythagorean triples, these contrived problems lend themselves quite nicely to it. But if you forgot one, you could always use the Pythagorean theorem here. So go ahead and write that out. The y squared is going to be 25 squared minus, that should be 7 squared. 7 squared is 49. Let me erase that real quick. Minus 7 squared. So y squared equals 625 minus 49. And let me see real quick in my head. 620, well, it's got to be 24. So 625 minus 49, that's going to give us 576, which is a perfect square. So y would be 24. So if you forgot that this was a Pythagorean triple up here, you can go ahead and use the Pythagorean theorem to figure out that missing length, just like we did there. So now we're going to have to set up an equation. So let's go ahead with that. Looks like we have what? We got an x squared, and x squared plus y squared is going to equal the length of that ladder squared. So I'm writing 25 squared here because 25 is a constant, right? This 25 is a constant. So it's not going to change, whereas my x and my y's, they are rates of change. They're going to be changing, right? So let's go ahead and implicitly differentiate. Got 2x dx dt plus 2y dy dt is going to be equal to 0. That's a constant, right? So when you take the derivative of a constant, that is always going to 0. So go ahead and we'll say that that's a 0. All right, next step is when we fill in some of the values that we know. So for instance, we know what x is. X is 7 and y is 24. So let's go ahead and fill those in. Oh, and I also know dx dt. So substituting 2 times 7, this is the instant when we're 7 feet away, times 2, that's the rate at which the ladder is being pulled away from the wall, plus 2, let's see, y was 24, and dy dt, that's what we're looking for. And this is still all equal to 0. Whoops, forgot to write my 0 up here. So go ahead, multiply those together, and I get 28 plus 48 dy dt, still equal to 0. So go ahead and subtract 28 on both sides here. So we'd have 48 dy dt is equal to negative 28. Then divide both sides by 48, and you're going to be well on your way to the solution here. Let's see, negative 28 over 48 equals, that reduces, divide the top and bottom by 4, negative 7/12. So this is going to be in feet per second because all the dimensions in the beginning problem were, as we can see, feet per second. So this, when the instant the ladder is 7 feet from the building, it is the top of the ladder is coming down the building at 7/12 feet per second. So the negative could mean that it's coming down, or it could mean that it's decelerating. Hadn't thought about that with this example though. But anyway, there you have it. You have two classic problems, right? You have the pebble problem, the pebble dropped in the pond, and you have here a ladder problem. So there's two good examples for you to check out. If you have any other examples that you want me to look at,
you can put those down in the comments below, or you know your publisher of your textbook, the author of your textbook, you can go ahead and put in a page number and a problem number, and I'd be happy to work some of those out for you. I have most of the textbooks, so yeah. So go ahead, please smash that like button. And don't forget that math is not a spectator sport. You do not have, you have to practice on these related rates problems.